Okay, so it's our pleasure to start today with a talk by Laura Murray on principles of group bundles and Freed-Quinn line bundling.
Oh yeah, thanks to the organizers for organizing this week. And yeah, thanks for the invitation to speak. So today I want to talk to you about a project on two groups and two group bundles. This is a joint work with Dan Berg-Evans, Emily Cliff, Kervin Nakate, and Emma Phillips. It started at like a AMS MRC like research community thing, and then yeah, some of the project is like with a subgroup of those things. But yeah, joint work with those people. And before I talk or tell you what two groups are and two group bundles are, I want to start by kind of giving a kind of a bigger picture and landscape of kind of like why we are thinking about two group bundles and why we care about it and why I would talk about it at a field theory conference. Okay, so something that maybe a lot of you care about, and so yeah, something that's come up in previous talks are gauge theories, like Chern-Simons theory. And I'm going to look at specifically digraph-Witten theory, which is really toy model for Chern-Simons theory, where your gauge group is finite. So you have a finite group G, and you have a 3 co-cycle. And you can describe this this gauge theory with it. Okay, so yeah, and part of the title of the talk is Freed-Quinn line bundle. So Freed and Quinn in paper in 93, they gave a nice description of this digraph-Witten theory as from a functorial field theory perspective using a line bundle. So find this line bundle. Over moduli space of G bundles on Riemann surfaces. So this is like their intermediate step for defining or describing what this digraph-Witten theory assigns to a surface. So yeah, if you have a Riemannian surface, sigma, they describe the value of digraph-Witten theory. I think the only used this is like the value for this script X for the value of the field theory on this surface, and it's going to be the sections of this line bundle where you evaluate at sigma. So sections. So that's something that I know pre-existed, most are not. Where our project comes in is noticing or like taking this input data for digraph-Witten theory and saying that you can also form this kind of categorical structure from it. So this finite group G and this alpha, those are exactly the input data that you need to describe something called a two group. I will be more specific about what a two group is in just this second, but kind of in terms of this motivating landscape like picture. For now, the thing to know is that it's a categorification of a group. So it's instead of having a set with a multiplication function, this bilinear operation, you have a category, and then you have your multiplication is a functor, and it satisfies higher compatibility conditions. Yeah, and you have the group axioms like associativity and unitality are like natural isomorphisms that you're about. So yeah, more higher category. I mean, by higher category, I just mean category, but category information than what you get for a group. Right. So yeah, this is this thing called a two group, and for a two group, you can define these principal bundles. Okay, principal bundle is two group G, sigma. And there's a forgetful functor from these two group principal bundles to ordinary G bundles. And this G is the group that this underlying regular group of your two group. And what our project was looking at these two group principal bundles where you're dealing with kind of like a weak notion of a two group. So there are different stricter notions that you could have. Yeah, dealing with the weak notion of a two group. We looked at isomorphism classes of the fiber of this forgetful functor, and show that those give you a U1 bundle that is going to be isomorphic to the U1 bundle associated to this line bundle. So it's kind of like a categorical description of this line bundle that they constructed using more kind of like transgression methods. So let's see. Here's a my sketch, and I'll say, yeah, some notes. So yeah, it's the fibers in the U1 bundle that's related to this story, like this story. The other thing to note, like for this audience maybe, is that these two groups, so these two groups in this like weak sense, Chris has a description of the string group as a weak two group where you have kind of smooth structures. So and as smooth two group, and for different people in the audience, for like the string group means different things. So I guess you have some choices to make of like how you want to model this string group. So sometimes when people talk about the string group, they're thinking about it as a group, or as a Lie group, but where they are dealing with things that are infinite dimensional. But this model says like, no, we want to have things finite dimensional. But in order to have things finite dimensional, you're forced to kind of move up category level. So you're forced to deal with something that's a two group instead of just an ordinary group. So that's kind of like also some of the motivation for looking at these two groups and these two group bundles is to say things about string structure in this finite dimensions setting.
I'm sorry, what's the difference between the NG of sigma and the bungee of sigma? Is the bungee before you model out by gauge transformations, or are those the same thing?
Right. So let's see. Yeah, those are they're going to be the same. So it's like, yeah, this NG when I evaluate at sigma is going to give you the bungee. Yeah. Any other questions about this landscape picture? Okay, so my plan for the talk is I'm going to kind of like zoom into different parts of this. So first I'm going to describe what these like two groups are. Right, one. And I'll describe what these two group bundles are. Right, two. And then I'm going to describe some of these different applications. So I'll give you a classification of these two group bundles, and I can describe how it relates to things like these different nodes here. So okay.
So yeah, just to be sure that I'm on the same page. So G is the finite group. So MG is just a collection of isolated sort of objects with stabilizers. So right, so like isolated types of G coverings with the isotropy groups, and over each point there is some sort of a fiber of this Freed-Quinn line bundle.
Right, and I guess that fiber is U1, and they do that by doing a pairing of it's like let's see. So yeah, you take this co-cycle and you're going to like pull it back along the. I think what you're describing is maybe like an automorphism of a principal bundle is like part of the.
Yes, so just my point is that MG is just it's doesn't have continuous moduli. It's
yeah, like point mod automorphisms
okay.
Yeah.
So it's very different from counting, like holomorphic sections of some line bundles. It's very different from that problem. Okay. Mm-hmm.
I guess that would be like yeah, you'd want to have a connection there, and you'd want to. But then it's like the pre-quantum line bundle. I think is that what?
Yeah.
No, maybe not.
I just wanted to be sure that the MG
yeah.
is just a bunch of points with stabilizers.
Mm-hmm. Another question. All right. Okay, so let's move into this kind of just like what are two groups, and we're going to be interested in talking about smooth two groups. But let me just start with the non-smooth case for I don't know as a warm up. Okay, so I think I'm trying to gauge like what the like the different perspectives in the audience. So there are different ways that you can describe what a two group is. So a two group categorifying the idea of a group is going to be a category where we have like the category version of this multiplication. So that would be like a monoidal category. Then we want to have inverses like you have in a group, and so it's going to be a monoidal groupoid. A two group is monoidal groupoid G. That gives you the inverses for the morphisms, and so then you also have to say that all your objects have like weak tensor inverses. That means if you have an object in your group, there exists another object where the things that you would have as inequalities, and if you were just dealing with an ordinary group, you now have these natural isomorphisms from the tensor product of G and G inverse to the unit object, and the opposite way around as well. It's kind of like hiding up a lot of information if you aren't familiar with, I guess, like monoidal categories before. But yeah, I guess like the general kind of like slogan that you can keep with you is that you're taking all the group structure that you have for an ordinary group, and then wherever you would have an equality in those group axioms, you're thinking of it as being like a some categorical information. So you have this like natural transformation. Maybe another way of saying this is that, or an equivalent way of saying this, is that a two group is a group object and the two category of categories. I guess here I'm using kind of like a weak group object. And there are different flavors of two groups. You can have strict two groups, like coherent two groups. I'm going to be dealing with like kind of like the weaker sense. You have these weak two groups. So yeah. Okay, so maybe some examples. Okay, so if you have an ordinary group G, you can think of it as a two group in a kind of trivial way, where the objects are given by the group G, and you only have identity morphisms. So two group objects. Morphisms. And the write this as G. Here's I guess it's like internal category notation. So yeah, here this top, I guess here's just this top set. This is going to be my my morphisms. I have these source and target maps to the objects, and here, yeah, they're just projection. So that's yeah, I know. First trivial example of a two group. Another way that you can make a two group from groups that you're familiar with is that if you have an abelian group, you can form this two group where you can do the opposite thing. Your objects are really trivial. You only have a single object, and then you have A with some morphisms. So I'm going to call this A. And yeah, here like the composition uses the group multiplication. Yeah. Okay, and then the last example, I want to kind of, I don't know, maybe a second example is actually no. I'm going to kind of unify these two perspectives. So let's do the following exercise. So let's start with a two group G. So start with this monoidal category where all the objects and morphisms have inverses. And let's extract some kind of ordinary group information from this. So given a two group, we can extract the following groups from it. So if we take the isomorphism classes of the objects, you get just an ordinary group G. Okay, so that's a group that we can get from this category. If you look at automorphisms of the unit object in the category, we get another group that's going to be an abelian group. Abelian group. And by taking, I guess like by conjugating the identity morphism for any object, by conjugating any automorphism of the identity with the identity morphism for any object, we get a group an action of G on A. So action. Okay. And then another thing that we have as part of the data of a two group, this category that we can write in terms of these groups G and A, is we have a 3 cocycle. So we have this map alpha. I guess it's a cocycle. And this cocycle condition, so this cocycle, this cocycle condition is it exactly comes from the pentagon axiom from the associator of the category, the monoidal category. Okay, so from a category perspective, you can get this group description, and I guess like group cocycle information.
So where does the alpha come from?
I'm sorry.
Where does the alpha come from? Like, how does it come?
So if I'm going in this direction, I'm starting with my monoidal category G, and it's the associator. So the alpha comes from the associator.
And like you just pick representatives, so is that what you do?
Right. So I guess the next statement was that if you choose, so yeah, this should be like H3 is maybe what you're saying. So like if you choose homologous things, you're going to get equivalent two groups. I'm first saying just the naive thing of like, yeah, given a group of this monoidal category, I want to extract information. But yeah, maybe going like related to Matthias's comment, there's a theorem. So I guess it's first due to since she was a student of Grothendieck, and it was in her thesis, so it was like yeah, an unpublished thesis of why is Lauda, so kind of just to look for it. Every two group is going to be of this form. Can be just classified by this quadruple of data, G, A, alpha, and this action. And I guess, yeah, these are made a more precise statement where if you had equivalent two groups, then yeah, this alpha should really be an element of H3 of G. Nice. And yeah, so we've sketched the construction from these category information to this kind of maybe more like group cohomology information. To go the opposite way around, you can build a two group from this information where you take G to be the objects, you take it to be a skeletal category where so A gives you the morphisms, and then this cocycle that you get functions in representative alpha. Because the cocycle condition is can exactly translate to the pentagon axiom, you get your all the data that you need to define a monoidal category. Okay. Any questions?
So you have a very strange question. So this collection of data, it looks a little bit like if you take a Postnikov tower of some topological space and bottom two levels, isn't it like a similar set of data? Let's give an example of a two group, I guess.
Yeah. Let's see. I don't know if this is orthogonal to your question. Are you possible? So yeah, you can think of this as like being an extension, a central extension.
So I have some pi1, pi2, and some sort of action of pi1 and pi2 and some extra sort of
I see. Okay. So you're saying, and then here, yeah. So it's like you're just seeing like the first two. Okay. Maybe one other remark I might say is that this information sits inside a sequence. I think maybe Brian Williams talked about these group extensions being classified by H2 of G with values in A, and here it's kind of like a similar result where these extensions, they're categorical extensions. So again, it's like now just this curly G is now just like group, but we're allowing it to be a two group. These are going to be classified by H3 of G values in A. And kind of this way, thinking of how these two groups of this particular form, how they fit into this extension, is when they come up again when we are talking about the string group. Any other questions? Okay, so we talked about, we talked about two groups. This is like without any topology. We want to eventually talk about smooth two groups. So let's see what happens when we add kind of like something smooth this way. So in this chart, we have on the top row is this this description that we've just done. So kind of going from classical to categorical, you start with things that you're familiar with from undergrad. You have this, a group is a set with a function of sets, group object, and sets. What we've done is we've categorified this. We're now looking at a group object, not in a category of sets, but in a two category of categories. So a two group is going to be one of these categories, and then this, it's not a function, but a functor. Okay, so that's kind of what we've described so far. Is that top row, you're also familiar with this column. So we can add topology to this story. So instead of looking at groups, you can look at Lie groups. It's a similar kind of thing. I know we're writing the same diagrams again. It's just what category are you thinking of the diagrams as being in? So a Lie group is going to be a group object in manifolds. So it's going to be a manifold that has this like multiplication structure that will be a smooth map of manifolds. Okay, so I've said that these are the things that are known. Now we want to fill in this bottom corner to talk about smooth two groups. So kind of like continuing this pattern of how we kind of categorify things. This should be a group object in some category of, I guess, like smooth manifolds. So again, sets to categories, manifolds to I said smooth manifolds to smooth categories. This multiplication functor should be, whatever this functor of smooth categories would be. To be more precise about what we mean by this category of smooth categories, I guess you could take this to be smooth stacks. Another thing is really down to, or a presentation of this would be taking this to be Lie groupoids. And I'm going to more be thinking about it in terms of Lie groupoids, but there I have to be careful about what the morphisms are in this category. So it's particular what this kind of multiplication functor is. And so I think this story might be familiar to some people. I want to kind of take an aside on what Lie groupoids are and what type of morphisms between Lie groupoids I want to take in this setting. Okay, so what is a Lie groupoid? So a Lie groupoid so it's going to be kind of like how we were writing our categories here in terms of objects and morphisms. We would do the same thing, but we were writing it instead of in sets, it's in manifolds. And so it's category internal to manifold. So we have a manifold of objects and a manifold of morphisms. We have all these source and target maps, psychic identity maps. So plus more data like composition map, satisfied conditions. But for people who are seeing Lie groupoids for the first time, the idea is that your source and target are not they're not sets, they're manifolds, and your objects and morphisms are manifolds, and your source and target maps are going to be surjective submersions in order to be able to make sense of things like the composition is taking the fiber product of x1 cross x1 over x0. So Lie groupoid is this diagram and manifolds. More precisely, it's like a groupoid internal to. Okay, so if this is your first time seeing Lie groupoids, what are some examples that you should keep in mind to anchor yourself? So every manifold you can think of as a Lie groupoid. I guess this is also kind of paralleling what we did for groups. You can think of it as a Lie groupoid where you only have identity morphisms. So M is a manifold. This is a Lie groupoid. Identity morphisms. What does this mean in this case? So it would here I would have X is my objects. I'm going to have X as my morphisms, but this the source and the target are just going to be the projection down to X. See, example 2. If you have a Lie group G, form we'll call the classifying space of the Lie group BG, Freed-Quinn G. So this is going to be this Lie groupoid where you have just a single object, and you have G worth of morphisms, the composition that is just given by multiplication of G. Okay. And the final example that's going to be, come up when we're talking about bundles and stuff, is a check groupoid. So if you are given a cover, generally, so yeah, if you're given a cover, you can form something called a check groupoid. So objects are going to be given by Y. So yeah, you have a point in your cover, and you have a morphism or an isomorphism between 2 points in your cover if they live over the same point in X. So this is going to be Y plus X plus Y. This is another Lie groupoid. Okay. Any questions? So now we want to talk about what. So our two groups are going to smooth two groups are going to be a Lie groupoid. So yeah, we have that part down. Now we need to think about what this multiplication map is going to be. So like, what are the morphisms in Lie groupoids? And it turns out that here there's like some subtlety involved. So first naive guess, thinking about like, okay, Lie groupoids, this is like diagram, it's internal to manifolds. I can just draw my my ordinary idea of what a groupoid would be, what a category would be, but I just think of everything as being in manifolds. Be like, okay, we should have our morphisms be kind of like the analogous thing. So our morphisms should be smooth functors. We do that. We draw what we would want a morphism between two, or a functor between two categories to be. But then think of everything as being a manifold. So it would be this pair of maps, these smooth maps, F1 and F0, and together these would give a map, a smooth functor F from this Lie groupoid X, this Lie groupoid Y. That's like, I don't know, that's a way that you could define the category, or that is the category of Lie groupoids. But it turns out in our case, that's not exactly the right notion of morphism that we want to have. So maybe some examples that illustrate kind of what goes wrong with taking this as the idea of morphism in this category. Some problems. So problem number 1. Let's see. Let's start with this kind of like check groupoid thing. So if we start with this cover, as steps, we want this check groupoid. So we'll say to a cover. We want this to be equivalent to X, which would be some sort of like resolution of X. But when we think about like what this would mean as Lie groupoids, this means that you would have looking for a smooth functor that fills in this diagram. So here, what is your map? Here's smooth functor from Y to X going to be. You can just take that to be the map by the cover U. And because X, when we're thinking of it as a a Lie group way, all the morphisms are just identities. This is going to be just decomposed with projection. I guess, yeah, either projection. And yeah, to say that we want this to be an equivalence means that we should be able to inverse this. I guess, yeah, and if we're thinking about the morphisms as being smooth functors, we want to find you know, this like smooth map, this section here. And I don't know, that's weird. Like if you have a cover and you have this type of section, it's a pretty boring cover. You have one of the elements in the cover has to be the whole full X. So yeah, let's see, this functor alpha, I'll call this F, this smooth functor F is invertible. If and only if your cover U has a section. Like it's too strong of a condition. Another example, or yeah, problem example. So I guess maybe this is just kind of taking out based on what I like verbally said the name is. So if we are thinking of this Lie group BG or Python G, if we're thinking of that as the classifying space, we should have that maps homomorphisms from X into G into this Lie group line. This should be equivalent to getting you G bundles on X. Yeah, what happens when we, so yeah, that's kind of like what we know it should be in terms of ASMA like stacks. Like, and let's look at more specifically when we have this presentation as Lie groupoids. Those Lie groupoids, what are the smooth functors from X into Python G? So I have X. So on objects, I have like no hope of anything interesting. I'm mapping into the point, so that's going to be like really trivial. I might say, okay, well at least on morphisms, I have a chance of having something interesting, but here we're also out of luck because all the morphisms in this source Lie groupoid, they're all the identity morphism. That's how you're thinking of X as a Lie groupoid. So if I have a point in X here, I really want to think about it as being like identity over the X here, and for this to be, this whole package to be a smooth functor, that has to be sent to the identity of the point here, which is just the unit object, the unit element in G. And so, yeah, we only get a single G bundle, the trivial G bundle, if we're asking for our maps from X into the classifying space to be smooth functors. So this is trivial G bundle. Next, I guess you get like interesting automorphisms, but yeah, you look at this trivial bundle. So, yeah, like both these situations, like a SAT, we want to have more than just, we want to have more morphisms than this. We want to get more bundles than this. We want to, yeah, be able to get this equivalence for, and yeah, when you have you don't necessarily have a section of your cover. And so if we think about kind of like what the problem is, or yeah, that's kind of in common for both of these situations. In both of these situations, we can say, okay, given a cover, yeah, I definitely don't want to always have a section of this cover, but locally, yeah, every cover should have a section, or every cover does have a section. A similar type of pattern happens here, where, yeah, we definitely want to have more than just the trivial bundle, but locally, every bundle is the trivial bundle. We have this like, I don't know, locally it's all good, and we want, but yeah, we just have to make this global problem. So what is, there's kind of like, I don't know, I guess maybe a general technique that we do when we want to do this local to global thing, like sheepify or localize. So that's going to be our solution. So, mean, like the heuristic idea of what this like localization is for people who are seeing this type of thing for the first time, is that we're like formally adding in morphisms that go the wrong direction. So now in this new category that we're gonna have like zigzags of morphisms, and that's gonna kind of solve some of these problems that we had of only getting trivial things. So we're gonna localize with respect to like what are the zigs of my zigzag. There be essential equivalences of Lie groupoids. So these are massive Lie groupoids that I guess like are kind of like the analogous of fully faithful and essentially surjective, but they kind of, have surjective submersion properties to kind of make them work nicely with the manifold aspect. And yeah, this is a result of direct prong that this category satisfies the things that you need in order to be able to localize. So this is my particular equivalence is something called W. I'm going to localize with respect to the weak equivalences, so formally invert these type of morphisms. And she says that this is equivalent to, I guess another way of presenting this would be as bibundles, if that's like the language that people, or if that is a language that people are familiar with. Okay. Any questions on this?
So what was the essential ones?
So it's I don't know if I want to write out like all the details.
Like on the example, maybe like can you explain on the example?
And then there is an essential.
Sorry.
This one there is an extension.
Yeah. So yeah. This let's see. I guess like any. So if this is a manifold, I guess like any essential equivalence into a manifold is always going to be on the formally checker. If I don't know, maybe that's not a helpful thing to say. Yeah, this one is an essential equivalence. I think maybe the helpful is it's like what an equivalence of categories would be these like a function that would give you an equivalence of categories would be fully faithful and essentially surjective. And it's kind of like the analog of that. You just have to be careful how you're describing this in terms of the fact that you're not dealing with categories, you're dealing with like smooth manifolds. And so if you have like these kind of extra like surjective submersion type of properties that involve these like pullbacks along these surjective submersions. But I think in terms of like kind of like the gist to take away from the talk is like, yeah, it's the analog, the smooth analog of fully faithful and essentially surjective.
So should I think of it like that you kind of invert the morphism in the first example?
Yes.
And
yeah.
then it like allows you to have all the G bundles from in the second example.
Exactly. So
Yeah.
I just made like the way of and then like what it's saying is that you can, instead of asking for a map from X to point on G, you're allowed to, you're looking at like this cover, like this resolution, and then yeah. Okay, so let's see, I want to get to the principal bundles story. So let me just say definition. This is due to this. A smooth two group is going to be a group object in this category of bibundles or this category of like the localization of these Lie groupoids. So we can fill that in here. And what does that mean? That means so I'm not going to edit this this like kind of schematic, but it means that this multiplication map, I know it should be like a zigzag of maps or a bibundle. So yeah, it's like a slightly like more information is hiding in that thing that's just drawn as an arrow. Okay. Before I talk about principal bundle, maybe the one last thing I want to note about just like these two groups is that this this description of two groups in terms of like this categorical extension, Chris also gives so maybe this is like an example of, I feel like it's like somebody achieving this example. It's not very explicit at all. But yeah, you can think of the string group as being a smooth two group, so being this group object and Y bundles, and is two groups. And it sits in this class of examples, so I guess, and here I'm from Chris. Categorical, so yeah, smooth, categorical central extensions of a Lie group. So something that fits in this diagram. Same sequence that we wrote there, but now thinking about it in terms of like these smooth two groups. I guess that's smooth group, Lie group. These are classified. So isomorphism classes. You can identify with the Siegel-Mitchison cohomology of Chibi A. Kind of like the analog of that discrete result that we had. And so you can think of string as like sitting in this case. In terms of this model for the string group as a finite dimensional but like smooth two group, it would be the central extension of spin n classified by generator in this. That's a way to connect some of the story to the string group and string structures, if that's kind of where your interests lie. Okay, but going back to let me get to these two bundles. Any questions? Right, so just like for ordinary principal bundles, but an ordinary group, there are many different definitions or descriptions that you could have for like a two group bundle. So I know people take like holonomy data, people take kind of like check data and so on. So I'm going to give, I think, like first quick definition of what a principled two group bundle is. And then I'm going to give a classification result in terms of check data. So I'm not going to unpack all the details that are hidden in this first definition, because I think it's like for our project, it's more helpful to think about this classification result, just for doing different calculations. But I think, yeah, a good first definition that really parallels the definition that you see for G bundles is that a principal, so yeah, let's see, a principal, so yeah, G is a smooth two group. Principal G bundle X consists of a Lie groupoid over X with an action of your group G that is locally trivial. So that means that there exists this cover that when you pull back, P along that cover, there's like this equivariant isomorphism here. And kind of similar, so maybe just, there. Want to get to the result, I maybe just will like very briefly note where complications are happening in this definition. That arise from thinking about these things as being in bibundles, like being in this localization of group weights. So here, this action, it's not like an action that you describe with a smooth functor. This action is a bibundle. So that's extra information in terms of like that zigzag. If you are thinking about it in terms of that localization story, if you're familiar with the bibundle story, like you know that this, involves this extra, manifold with these anchor maps that tells you the data. It's part of the data of action that then has to satisfy at least compatibility conditions. And kind of a similar thing here. This arrow is really hiding a lot of information. This arrow is a G equivariant bibundle. Yes, bibundle, so it's already more information. The G equivariance is also more data here. You have this like higher compatibility conditions that are really being hidden in this this definition. So for the sake of time, it's just like the slogan is that you can define these principal two-group bundles in a very analogous way. But there's more complications since we're dealing with this localization. Let's see. Maybe one more before the classification. So with the kind of like the general like the goal of this project is to understand this moduli problem of how we get to these G bundles in X. So I guess I'm going to look at what the morphisms are, but these are kind of like objects of this category of G bundles. X. We want to understand this moduli problem, and our strategy is to look at like the simpler problem of looking at association to just the trivial G bundles, and then stack it. So this is joint or work in progress with the first two authors that are listed. So Stackify Evans. This is in progress. Showing that when you Stackify, you get this. Evans, really flip. Part of the thing that goes into showing this is as you're dealing with kind of like this description of what a two-group bundle is, you have these these I guess trivializations, of this pullback to Y cross G, and then you have to check that it's compatible, and if you have like different pullbacks, and so this involves showing that you have an equivalence of monoidal categories in these G equivariant automorphisms. Y. To these maps of Y bundles. And in this case where we're dealing with these like these weak two groups in in Y bundles, the equivariance data is kind of like the nuance of or like the interesting thing in this result is like how you construct that given just a map of Y bundle from Y to G. So that's what like kind of goes to these results go to I guess our interest in this like classification in general for smooth two groups that come from these extensions of any like of a Lie group. We have a result in the discrete case. This was the result from the MRC group at the beginning. So in the discrete case where your G is of the form is this two group associated to a finite group. We can work out this kind of this description in full. So how does this work? So might be familiar with, you have, so again, I mentioned that you have different descriptions of what bundles are. So we have this description of a principal bundle, G bundle, ordinary G bundle over X. You can describe this, it's determined by check data, so it's determined by a cover. And then it's like transition data on intersections of the cover. So you can think of this as being a cocycle. Cocycle. That means that it satisfies this rho of y1, y2, rho of y2, y3 equals rho of y1, y3. That's like the classical story. In the like two group story, we can show an analogous thing and show that these two group principal bundles, they're determined by the same data as before. So because you have that underlying G for your two group, you have a cover, you have this cocycle. But then following this category theory philosophy here, where you have this equality and this like cocycle, for this cocycle, in kind of two group plane, you don't have or I mean, I guess they're equal as elements in G, but you have an isomorphism. You have an element in A that witnesses this. So you have call it gamma to be like that. The isomorphism between these two objects, or yeah, the isomorphism of that object, Y, B, A, and that this gamma satisfies this condition that B gamma equals rho star alpha. Okay, so and yeah, this is just like on objects. We kind of have a similar description in terms of morphisms and I guess morphisms in the two group principal bundle case. But again, made an upshot. Is that we have this forgetful functor. And to me, in this presentation, it's really clear. You have this forgetful functor from two group principal bundles to ordinary G bundles. Given one of these, like U gammas, you just forget that gamma. And so, what does this mean? That this means that we can describe the homotopy fibers, the fibers of this forgetful functor. Okay, so yeah, we have this functor, right? So yeah, we show that it's a vibration, and then you can describe that the homotopy fibers of this functor in terms of these elements gamma that trivialize rho star alpha, so that elements gamma where G gamma is rho star alpha. Maybe I'll say something else. Right, so if we have a G bundle X, its fibers are going to be equivalent to trivializations of rho star alpha. So you can think of this rho star alpha as being like a flat two-germ. That's the language that you are familiar with. I mean, I won't say what that is if you're not familiar with it, but yeah, it's like this rho star alpha. It's this map from Y3 to G, and Y4 to G. And then this is saying that gamma trivializes it is like exactly this equation that we have here. And so it's kind of like how this argument works. So if we have a P in a principal G bundle, we're going to think about the associated U rho. Maybe for the sake of just getting this sketch up, put aside the cover and just be thinking about this cocycle data. We can get these covers by doing yeah, a localization. So I know it's almost like two separate processes. So you have this this row, you want to say identify these this homotopy fiber with these trivializations. So what is the homotopy fiber? The homotopy fiber consists of the row 1 gamma 1, and then has an isomorphism to the row that you're interested in, and using with a very explicit description and calculation defining is the row is already given, but yeah, defining this gamma that lifts it, and defining the data that you need for this map. So that is blank, the data that you need there. And these two pieces of information come very explicitly from the alpha that you have for your two group bundle or your two group, and gamma 1 and exact conditions that you have when you know that you have an isomorphism here. So yeah, it's a really explicit calculating co-cycles description.
Can I just ask, because I've been puzzled by this. So is this equation that you're requiring, this d gamma equals rho star alpha, that's an equation over what? Over y4?
Yeah.
Okay.
So I guess maybe that
If you have y4, you have like the three elements that you get sort of from.
right. I guess it's like coming from like, so yeah, you could generalize this maybe like for a Lie group point X instead of just a manifold X, or but then yeah, so like this is thinking of
I guess I was.
you have a question, I guess maybe like thinking about it as like this thing that comes from this, and then like what is this? This is like y2, y. I don't know, is this where the question comes
No, I
from?
think I was having a hard time compiling this equation, like the two, well, what those two objects are, and they're maps. They're both maps from y4 to a. Is that right?
Yeah, right.
Okay.
Any other questions? Okay, so I think I'm maybe out of time. Maybe just like final like 2-minute comment to again maybe this will connect with Matthias' talk next, but so yeah, what is this? So this description of these two group bundles that are lists of an ordinary G bundle as like trivializations of this like rho star alpha. You can think of this as like giving a description of I guess yeah, or connecting two different descriptions of what string structure should be. So I just made like the caveat that I think is different from what you might be talking about is that in this case it's discrete. So for the string group that smooth string group that Chris describes, I mean you have always a forgetful functor from bibundles to just groupoids, forgetting the topology. So yes, in the discrete setting, if you have a flat vector bundle V over X, I guess I'm using notation, I'm going to write V as like this classifying map. Like your ON frame bundle, you have this when it's flat, you have this reduction to this is the discrete version of ON. And you can think about string structures as being this lift, flat string structures. I mean, yeah, you could hopefully tell us, or yeah, aspirationally tell the story, there's things to make sense into non-flat things. But yeah, you have this flat string structure, you have this the discrete version of the string group living over this discrete version of ON, and you could describe flat string structures as lifts. So these would be like bibundles, but there'd also be like in this lift, there's also two community data. So there's like this higher categorical data, and yeah, you describe these as flat string structures. And I guess yeah, this would be saying that you have this lift to a string bundle over a given fixed bundle, and yeah, this story would hopefully relate this to trivializations of two groups, I don't know, maybe, so string structures in the sense of Waldorf in terms of, maybe like trivializations of the string, Simon's two. I think I'll end here, thank you.
One categorical case, there's a description for flat vector bundles in terms of side maps out of pi 1 to G. Do you have anything in this sense here?
Yeah, so, let's see, so I guess like in the, maybe like in the flat case, so I mean, it's like, would be like another row in like this description, so like you could have it in terms of like, that's like the holonomy data of, so yeah, you have that in, I don't know, in the classical case, yeah. Wait, is this what you're thinking about? And yeah, so you could ask for a similar thing. Really G, and I guess this works if you have, if X is a like K by 1, otherwise you'd have to use like a higher category version of this, like a fundamental group or something instead. But yeah, I feel like we don't, that's like, yeah, a good question. That's like something that we would be interested in studying, but it's different.
You always guess would be pi less or equal to 2. Is that correct?
I know we haven't, I don't know if I know confidently enough that I can say like, yeah, we know how to go from this story to that story, but yeah.
In the real connection, you should take for X, you should take the drop space of X.
Maybe a question to like the thing you said last, so like this like sort of flat string structure. So what's the class? So you have this classification result for like basically flat string structures, right? It's the trivializations of this co-cycle. So what does that mean? Like how many are there in this case?
Sorry, for flats, since,
Are they like classified by H3 to like with values in discrete U1?
yeah.
Okay. H2, I guess. Okay. Mhm.
I said the flat is just like saying that you are taking the discrete. Yeah.
Okay, that's pretty much, but is there like a nice story or relation if I wanted to think about?
Probably, I don't know if I don't know, or yeah, I'm not sure what the answer to that
You're
one.
mixing two terms. You're mixing vector bundle and principal bundle. So which one would you like?
I'm wondering if there's like an analog of like pure dog over. Like it's. Talking about like having a vector bundle.
Let's see.
So if
I mean, is that the same as,
vector bundle is, then I'll tell you in like half an hour.
Yeah, maybe just a comment like there was this wrong research program, which is sort of program that I come from, John Byers and the higher gauge theory and everything.
yeah,
And what I like about this is that it somehow it fills in some gaps there that program never really did, and somehow this unifies the whole picture somehow. I'm not sure, like there was important gaps there.
yeah, I feel like, I mean,
Yeah.
you're the expert, so you can tell me if this is, but I think maybe a way of characterizing what they're doing, what you're doing is like and the difference is that you're doing things with like strict two groups, and so you still have to do things with like infinite dimensions, like so you're still, I don't know. And then yeah, this is like things with like
Definitely that, yeah, but also other things
Yeah.
that this fills in a lot of gaps, I think. Yeah. So this is able to tie a bunch of different pictures together, I think. Yeah.
So could you just comment a little bit more on this, like infinite dimension and strict versus like finite, because I didn't understand that and it sounds very interesting.
Like I might say talk to Chris, like yeah,
Okay.
so it's I say you know that like you have like know kind of like what you want your string group to be in terms of like a free connected cover of spin or something. So but you have like different ideas. Is correct? Like you have different choices of how to like realize that, and one choice is like yeah, if you want it to be a group, a Lie group, you have to deal with infinite dimensions. But you'd say no, you want to realize that it's a higher categorical thing that has the same like connectivity properties.
Like you could
you have B spin, you know, the classifying space for spin structures, B spin n. And you know what the next layer in the Whitehead tower is, so you know what B string is. Then the question is there a group or something that is string so that B of it is the
Yeah.
space you want? So there's no finite dimensional Lie group that will work. There are infinite dimensional Lie groups that can do that. And other models as like infinite dimensional topological groups that will work. This is like a higher categorical group that also works, that's finite dimensional.
I see, okay.
So there's sort of a trade-off. And now, you know, then you wanna like do things like figure out spinner bundle and stuff like that. You might hear more about stuff like that.
Yeah.
Next
So,
talk.
so I guess that what you were tapping into is like that there's, like there are strict models for the string group, like as a strict two group, but, they all use like infinite dimensional manifolds as like G0 and G1. And the point of like Chris's model is that you can, or like, yeah, that you can just use finite dimensional things if you are willing to work with non-strict.
Yeah, okay. Yeah, thank you.
I think we should thank Nora again.